We learned about the control hazard in the previous class, right? So what are control hazards? So if clock cycles are wasted by control instructions, like branch instructions, jump instructions, and exception, okay? Then, so it means that the PC, the control instructions change PC, the program count values. So if clock cycles are wasted by these instructions, then we call this situation as a control hazard, right? So I explained why the control hazards happen in the pipeline processor, right? It's because so we don't know. So actually, in order to execute a branch instruction, so then this is the example. So I will take the branch instruction as an example of control instructions. So when the PC is changed by a branch instruction, then I explained that we need to know the result of this branch instruction, and we need to know the target, right? But the problem is that the target and then the result of branch instructions are resolved late. Okay. So when the branch instruction, for example, when the result of branch instruction is resolved, then the pipeline, so some other instructions already fill the pipeline stages, like the instruction fetch or instruction decoding stages, right? So if these instructions are incorrectly fetched, then we need to cancel these instructions. And then I explained that this is a control hazard, right? So, and then also because the clock cycles are wasted by control hazard, so it means that we need to reduce the number of wasted clock cycles, right? So how? Actually, I explained that in this chapter and then in this course, so our processor, the processor in the textbook just supports EQ only. So which means that we can just add the equality check logic, okay? Equality check logic. Okay, it's okay. So which means that the result of a branch instruction can be resolved in the ID stage, right? So which means that, and then the next, so which means the next PC. So we can get the next PC in when the branch. Okay, so can you hear me? Okay. 아니 이것이 왜 이렇게 건전지가 빨리 닳아요? 도대체 왜 그런지 모르겠네. So the first way to reduce control hazards, so we can add the equality check logic in the ID stage. So which means that the result of a branch instruction is reserved when the branch instruction is in the ID stage. Okay, so branch is here, and then so which means that we can get the next PC. Okay, next PC when the branch is in the ID stage. So which means that if the next PC is the target of a branch instruction, so which means the instructions the instruction in the instruction fetch stage, this is the incorrect instruction. So we just cancel this instruction only, okay? But I also explained that because of this equality check logic, so this approach causes also another data header, right? So I explained that why, because the forwarding box is in the EX stage. So which means the result of previous instructions cannot be forwarded to the branch instruction. So that is the problem. So that's why I don't like this approach. So actually, we can add the dedicated branch unit like this. So which means that we can just perform subtraction for branch instruction, right? So PQ or BNE and BLT and BGE. So if we just perform subtraction between the RS1 and RS2, then we can get the result of the branch instruction. Okay, so we can get the result in the when the branch is in the EX stage. Also, if we use the dedicated branch unit, then the delay of this dedicated unit can be shorter than the delay of ALU, because the ALU needs to support some more complex computation, right? So, and then also the ALU needs to support various computations. So ALU, the logic is more complex than this subtraction logic. So that's why we can say that the delay of this dedicated branch unit is shorter than the delay of ALU. So in the clock period like this, so here, so this is the clock period, okay? And then we can say that, the result of branch instruction by this dedicated branch unit can be settled at this point, but the delay of the ALU is long. So the result of ALU is determined at this point. So if the branch result is determined at this point, then we can know. So and then we have this time period. We have available time period for until this point at the end of the clock cycle. So here, so we can get the next program counter value, and then this program counter value can be delivered to the PC register. Okay, and then it means in the next cycle, the new instruction, the correct instruction can be fetched. Okay, so if we use the dedicated branch unit, then actually if the branch is taken, which means that the condition of a branch instruction is true, then we just waste 2 cycles, right? Because the instruction fetch and the instructions in the instruction fetch and ID stages will be flushed. Okay, that's what we learned in the previous class. So then, what is the problem? What we want to reduce the penalty. So which means the wasted clock cycles by branch instructions more. Okay, so it is related to the performance, right? So if the branch is taken and then more cycles are wasted, then the performance of this processor will be degraded, right? So we need to avoid this situation. So which means we want to reduce the penalties by branch instructions more. We want to reduce, right? So, and then when the branch is executed, then we need to know firstly the result. Okay, result of branch instruction, and then the target. We need to know the target of the branch instruction. So if we know these two results, the outputs of branch instruction, then we can perform the branch instructions correctly. Okay. The target is it's easy. It's a relatively easy because we can calculate the target of branch instructions like PC plus immediate, right? So which means so we can get immediate value from the instruction, right? So immediate value is just included in the instruction, and then PC, we already know the PC of this instruction. So we can easily calculate the PC plus immediate, and then also we can get the result of PC plus immediate when we know the instruction. Okay. So which means that we can know the target of the branch instruction in the ID stage. But if the branch is resolved in EX stage, then if the branch is taken, then 2 cycles are wasted. So we want to reduce this penalty more in order to increase the performance of the processor. So we can apply the new technique called prediction. Okay. So the prediction instead, so we don't know the future. So the result of branch instructions will be determined when the branch instruction is in the EX stage. This is the future, but we can predict the future event based on the previous events, right? So for example, so we don't know the future, so which means we cannot know the weather condition exactly, right? Because this is the future event. But based on the past events, the past weather or some environmental cloud, now we can just predict we predict the weather, right? And then it's the same for the processor. We don't know the exact result of the branch instruction until the branch is executed in the EX stage, but we can predict. So for example, think like this. So for I equals 0, then I less than 100, and then I plus plus, and then some functions here. Actually, if we see this code, then we can easily know that, oh, when this code is executed, and then this function will be repeated 100 times. Why? You can easily know the behavior of this code because it will be repeated 100 times. So firstly, and then we can implement this iterative for loop with the branch instructions, right? So the EQ and then something there, and then return to some target, the first target of the branch instruction. So we can implement this for loop like this. Okay, this is the target. So if we just focus on this branch instruction, right? And then firstly, the branch will be taken. So which means that the result of branch instruction is true and true. Then the 100th iteration, it will be false. So actually, the real result of the branch instruction will be reserved and the branch instruction is in the EX stage. However, we can just we can predict the result of branch instructions if we just monitor the previous event, like the true. Okay, we can just monitor previous event, then we can predict the result of branch instructions with high probability. So this is very important. We can predict the future, right? And then based on this prediction, then we can just use this predicted result. If the prediction rate is high, the probability of this correct prediction is high, then we can use this result, right? So for example, you can buy a lotto, right? But the prediction rate is very low, extremely low actually. So that's why we do not buy lotto, right? Because the prediction rate is very low, we cannot buy lotto because that is the waste of money, right? But if the prediction rate is very high, then we can count on this prediction result. And then the processor can work based on the prediction result. Okay, so and then this prediction approach can be applied to the branch instruction, and then this prediction method is called the dynamic branch prediction. So dynamic branch prediction just predicts the result of the branch instruction. Okay, based on the previous events. Okay, that is the branch prediction. So I explained that if we can know the result of the branch instruction, but we can know the result of the branch instruction and the branches in the EX stage, so we can predict the result of the branch instruction, and then based on this prediction result, then we can use the next PC as the PC+4 or the target of the branch instruction. Okay, so this is the prediction approach. So actually, in the processor, so in the modern processor architecture, we frequently use these prediction approaches in order to increase the performance of processor. Actually, this is very important technique. Okay, and then we really apply these prediction approaches in the processor architecture. Okay, and this is the one of the prediction approaches. Is a dynamic branch prediction. Okay, so then let's see how can we predict the result of a branch instruction. Actually, it's very simple, right? It's very simple. So for example, so I mentioned that in order to predict the result of the branch instruction, that we need to monitor. We need to monitor the previous events of this branch instruction, right? So in order to monitor, so you need to monitor, okay, the previous events. Then what is required? In order to check the previous event, then these events need to be stored, right? Obviously, right? So in order to check the previous event, then the result of a previous event should be stored, okay? So for this purpose, we require buffer. we require a buffer that can store the result of previous result of this branch instruction. Okay, so we can use the 1-bit buffer or multi-bit buffer, like the n-bits buffer. Okay, so 1-bit buffer means that for this branch instruction, we just store the just one previous event. Okay, so if the previous event is true, then we can expect that, oh, the next event can be true. Or if the previous event is false, then the next event can be false. So that is the 1-bit prediction. So 1-bit prediction means that for each branch instruction, like a BQ, then each branch instruction has 1-bit prediction buffer. And then using this 1-bit prediction buffer, we can just store the just one previous result. And then based on the result, we just expect that, oh, the future result can be the same to the just previous result. That is the 1-bit branch prediction. Okay. So, and then it's very actually efficient, right? So for example, the for loop, like the for loop here, for I is less than 100, and then here the function is here. So branch instruction is here, will be here, right? Will be here. So for this for loop, then the event, the result of a branch instruction is, so it's jump to this point. So event of this branch instruction is true, 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 and true, false. Okay, so this is the previous event, right? So we can predict that, oh, the future event will be is the previous, then the future, just the prediction. Oh, this is true. So, oh, it will be true. Then, oh, it's the prediction is hit. Okay, so hit means that if the prediction result is equal to the real result, then it is called hit. Okay. Now, if the prediction result is not equal to the real result, it is called a miss. Okay, hit or a miss. So for the 1-bit branch prediction, so we just check just one previous result. So this is true, then it will be the future event for this branch instruction will be predicted as true. And then it's hit. So it's a hit. And then it's also predicted as true. It's a hit. And then it's a hit. Then predicted will be predicted as the true, but it's false. It's a miss. So for this 1-bit prediction, and then if we just apply 1-bit prediction for this iterative loop, then the hit rate is actually very high, right? So, and then if the prediction rate is very high, then we can just apply the prediction approaches. Okay, so then how can we identify the branch instruction? So I mentioned that for this branch prediction, then I explained that we need to store the result of a branch instruction, right? Then how can we identify the branch instruction? How can we identify a certain instruction? We can identify a certain instruction using program counter. right? So the branch instruction will have also a program counter for its own program counter. So for example, this program counter of the branch instruction is the 100, and then it's BQ. Then using this, so we can use this program counter as the index of the branch prediction buffer. And then for this branch prediction, we just store the 1-bit history buffer. Okay. And then this history buffer is indexed by this PC of the branch instruction. So for example, so BQ is here. This is the 0x100, and then another BQ is here. And we can just track the previous event like the 10200, 200. So, and then this prediction buffer is indexed by 100, right? So it is using this program counter, we can access this prediction buffer. Okay, so this looks like the memory. Okay, it looks like the memory, and then with the index of this one, we can access this buffer. So like the buff 100, and then for this branch prediction, branch instruction, then we can access the history buffer of this branch instruction like the buff 200. Okay, can access so using the program counter, we can identify the branch instruction, and then indexed by this program counter, we can access the branch prediction buffer. And then, so 1-bit branch prediction means that each branch instruction has 1-bit prediction buffer or history buffer. Okay. So, but actually the PC bit is the 32-bit, so which means that the PC is very large. So actually we just use the part of program counter for identifying branch instruction. So, but if this is the prediction, the prediction can be wrong, right? Prediction can be incorrect. So this is the case. It's a true, and false. And then actually for this case, the prediction will be incorrect. So then what's the problem? If the prediction is wrong, then we can cancel the incorrectly fetched instruction, right? We can cancel. Okay. Then we can fetch the correct instructions again. So if the prediction is wrong, it's okay. So actually the result of the processor is the same, but only the performance is degraded, right? So that's how the 1-bit prediction is working. But 1-bit prediction can exhibit the low hit rate. So what is the hit rate? So I explained that when the branch, this is the predicted result, and then this is the real result. And then if the predicted result is same to the real result, then this is the hit case. And then if this predicted result is not same to the real result, this is the miss. So hit rate means that the total prediction count, and then the hit cases So hit count is divided by total prediction count. So this is the hit rate, right? So if this hit rate is very high, then the performance will be good. Okay, but if the hit rate is low, then it means that the prediction is good. For many cases, the prediction result is not equivalent to the real result. So that means that the hit rate is low. So if the hit rate of a branch prediction is low, then the performance can be degraded because the clock cycles are wasted by control hazard. So we can use, I explained that we can use the 1-bit predictor. So which means that with the 1-bit predictor for each branch instruction, we just monitor just one previous result, okay? And then the future event of the branch instruction is just predicted using this 1-bit result. The problem of a 1-bit predictor is that the hit rate can be low for certain cases. So this is the example. So we can use the nested loop, like the for I is less than 100, and then inside of this for iteration loop, we can use the another for loop. Okay, and then we frequently use this nested loop, right? And then if we use the 1-bit prediction, okay, then the branch instruction will be here. So it's a branch instruction 1, and then the branch instruction will be here. So this branch instruction is for the outer loop, and then this branch 1 is the branch instruction for this inner loop, right? Then what will happen? So this is the branch 1, and then branch 2. So with the 1-bit prediction, and then let us assume that firstly the predictor predicts the result of a branch instruction as false. Okay, so this is the prediction, and okay. So I will just stop. Okay, so we do not have enough empty space. So this is the branch 1, and this is the branch 2, and this is the predicted, and this is the real result. This is the predicted, and this is the real result. Okay, so firstly, for the branch 1, so this is branch 1, then this is the inner loop. So it will be predicted as a false, right? And then what is the real result? It needs to jump to the first instruction of this iteration loop, right? So it jumps to this iteration loop. So real result is true. So this event is miss. Okay. Then what is this prediction? Because with the 1-bit result, with the 1-bit predictor, if the just previous result is true, then it will be predicted as true, and then it's true. Okay. So and then finally it will be predicted as true, but the real result will be false. Then what will happen for this branch 2? Then after this nested loop, then the processor will encounter branch number 2 here, right? Then it will be predicted as false, but it's true. Right. So and then for this branch instruction, how about for this branch 1? After this branch 2 is executed, then we will just encounter the inner loop again, right? You understand? Huh? So it was false, so it will be predicted as false again. But the real result, when the branch 1, this inner loop is firstly executed by for the next iteration of the branch, the outer loop, then it's true. So what's the problem? So this is the myth. This is the myth. So do you understand? So for this nested loop, if we use 1-bit predictor, then it is always missed. And then for the after the outer loop is executed, then the inner loop is again it's missed. It's again. Okay. So and then this event will be observed repeatedly. Okay. So do you understand? So this is the some shortcoming. So which means that for this nested loop, so and then in the real program, we can observe this nested loop frequently. We frequently use nested loop, and then if these cases are observed frequently, and then for this case, if the branch prediction is always missed, then the performance will be also low. So which means even though actually 1-bit predictor just monitors the just previous result, but some branch instruction like the BR1, the future event is determined by some many previous results. So if we just monitor the more previous results, then we can increase the hit rate of the branch predictor. Okay. So in order to avoid this case, we can use 2-bit predictor. So 2-bit predictor, as you can see, the 2-bit predictor has 2-bit prediction buffer per branch. Okay, and then this 2-bit prediction buffer works like saturated counter. So what does that mean? So this is the counter. So it's a 2-bit. It's a 2-bit. So this bit number is bit for this state is 0, 0, and then this is 0, 1, 1, 0, 1, 1. Okay, and then with the 2-bit predictor, if the branch is really taken, then this value is increased. So this value is incremented by 1. So it becomes 0, 1. And then if it's taken again, it becomes 1, 0, taken again, and it becomes the 1, 1. But if we use the normal counter, and then it's taken again, then it becomes 0. Like 1, 0, 1, 1, and then 0, 0. Because 1, 1 plus 1 equals 0, 0. Actually, so 1, 1 plus 1 is the 1, 0, 0. But this is the 2-bit number. So this is removed. So it becomes 0, 0. Actually, if we use the normal counter. But the 2-bit predictor use the saturated counter. So which means that if the 1, 1 plus 1 is actually, it becomes a 1, 1. Okay, so that's why this counter is called the saturated counter. So 2-bit predictor use the saturated counter. So if you see this diagram, so you can find that the 1, 1 state is the 1, 1. But if the branch is taken, so it is the result of this result, 2-bit predictor buffer is still 1, 1. Okay, so it works like the saturated counter. And then if a branch is not taken, so this means it's false, right? It's false. Then the number is decreased by 1. So for example, it was 1, 1, and then it's not taken, it becomes 1, 0. Not taken, it becomes 0, 1, and then not taken, it becomes 0, 0. Also, when the branch predictor buffer is 0, 0, then if the not taken again, it still remains 0, 0. Okay, so this is the saturated counter. And then, so this is the branch predictor buffer. And then if the buffer result is 1, 1, 1, 1, 0, then branch instruction is predicted as taken, which means true. And then if this prediction buffer is 0, 1, 1, 0, 0, then this branch instruction will be predicted as not taken, so it means false. Okay, so this is the 2-bit predictor. So with the 2-bit predictor, using the 2-bit predictor, so we can just monitor the 2 consecutive previous results, right? So we may, it's not always, we may increase the hit rate of the branch instruction, a branch predictor. Okay, so for this case, so we can apply 2-bit predictor for this case. So for the last iteration of this inner loop, so it will be predicted as true, but it's false. The real result is false. But if for this inner loop, then branch 2 is taken, and then we can just encounter this inner loop again, right? For this case, it is still will be predicted as true with the 2-bit predictor. You understand? So it is because for this branch prediction, the prediction buffer value can be 1, 1, right, at this point, and then it becomes 1, 0, right? So 1, 0 here. And then the prediction buffer is 1, 1, 0, but it will be still predicted as taken because it's 1, 0. So it's taken. So for this nested loop, we can just observe the prediction miss for only this case, not this one. You understand? So actually the prediction is a new technique. Okay. So but actually in the real world we frequently use the prediction approaches, right? And then which means that if we can predict the future event with the high probability, then we just execute some task based on the prediction result, right? because the hit rate is high, then if the prediction will be true, can be true, not will be, it will be 100%. Prediction can be true with a high probability, then it's okay. So we just execute this test already, then it's okay. But it's no harm. It means that, oh, if the prediction is wrong, then we can cancel. We can cancel our task, and then we just restart our task again. Okay, the prediction, if the prediction rate is very high, then we can apply the predictions. So in the real world, we can also apply the similar approaches, right? So for example, you can study computer architecture for the next lecture, because it's 100% prediction. The hit rate can be very high, so we can just study the next lecture.
For the 2-bit prediction, on the very first and second iteration, will it predict false for those first two before it predicts true then?
Is a true, you mean this case? Or
yeah, in this example, for the very first iteration and the second of the inner loop, will it predict false?
True. It's true. It will be predicted as true.
In the beginning, I mean.
In the beginning, it's the first iteration.
It will
and
predict
then
false.
Yeah, it's a false.
And then would it predict false again for the
right. Yeah, you are right. So it's a good point, right? But for the first iteration, so it should be false again. So it's a good point. Okay, it should be false, right? Because initially, I assume that initially the prediction buffer has 0, 0. Okay, and then the real result is true, then it will change it to the 0, 1. Okay, and then if the prediction buffer value is 0, 1, then it will be still predicted as a false. Okay, so you are wrong. And then also this will be missed, and then missed, but only for the first iteration. So and since the second iteration, it is hit. Okay, okay, good point. So actually the branch predictor is in the instruction fetch stage. So for example, so in the instruction fetch stage, so actually the detailed architecture is not exhibited in this slide, but we have the branch prediction buffer here, and then this branch prediction buffer is indexed by PC. So actually the part of the PC, and then we can get some prediction result. Okay, prediction result like the true or false, and then based on this result, we can predict the result of the branch instruction. Okay, and then at the same time, with the PC, the instruction memory is accessed, then we can get the instruction. So this is the instruction fetch stage. So actually, if we locate the branch prediction buffer in the instruction fetch stage, then we can get we cannot get. We can predict the result of a branch instruction in the instruction fetch stage. But what is missing? Target. So we don't know the target. Okay. With the branch prediction buffer, we can predict the result of a branch instruction, but we still do not know the target of a branch instruction, because we can get the target of the branch instruction when the instruction is fetched from the instruction memory. So we also need to predict the target of the branch. Right. So because the branch prediction buffer is in the instruction fetch stage, so we can predict the result of a branch instruction in instruction fetch stage. But in order to fetch the instruction, then we need to know the target of a branch instruction. How? How? Can you predict? We can predict. So in this example, we can observe that actually the branch instruction, these branch instructions are repeatedly executed, right? So we can observe that branch 1 and branch 2 are repeatedly executed because this branch instruction is in the iterative loops, right? Do you understand? So which means actually at the first execution, we can get the target of a branch instruction. So the PC is the same, because it's the same branch instruction, and then immediate value is stored inside of the instruction. And then for this same branch instruction, actually the target of a branch is the same, right? The PC is the same, and then the immediate value is the same. So which means that after the first execution, we can know the target of a branch instruction. You understand? So the target of a branch instruction can be also stored. So buffered. Okay? Because after the first execution, we can know, but this information needs to be stored. In order to use the previous result or previous information, we require memory components. So it means that we need to store this result. So target of a branch instruction is also stored. Okay, it is called the branch target buffer, or BTB. Okay, so BTB stores the target of a branch instruction, and then also the BTB is indexed by PC. Okay, so using the PC, the BTB, branch target buffer, is indexed by PC, then we can get the target. Okay. So in the instruction fetch stage, with the PC, we can access branch prediction buffer. So we can get the result of a branch instruction. And then also with the same PC, we can access branch target buffer. Then we can get the target of a branch instruction. So in the instruction fetch stage, we can predict, not really get. We can predict the result, then we can predict the target. We know everything. So then with the prediction result, then PC will be updated. So with the branch prediction buffer and then with the branch target buffer, then we can reduce the control hazard. So this is very important very important technique in the process architecture. We really use these prediction techniques, the many prediction techniques in our process architecture. Okay. So do you understand? Okay. Good. And okay, so and then so I briefly also actually this is the last part of the control hazard for exception. So when I explained about the control hazard, so the control hazards can be caused by branch instructions, jump instructions, and exceptions, right? And then I will explain about the exceptions. So what are exceptions? Sometimes we can use the terminology interrupts or exceptions. So actually, the meaning is a little bit different, but actually the exceptions or interrupts are handled in process in the processors in the similar way. So what is the exceptions? So as you can expect, the exception means that it's the unexpected event. Okay, unexpected. So for example, so like we can execute the instruction like the A equal B minus C, and then T equal 100 divided by A. We can execute this instruction, but as the problem, if the A becomes 0, it's divided by 0. But it depends on the values of B and C. So it depends. Actually, the programmer do not know which value will be assigned to variables B or C. It should be, yeah, it will be decided in the runtime. Okay, we don't know, but sometimes our program can encounter unexpected events like the divide by 0. So this is some example. And then sometimes when we access the arrays, then we keep the index of the array can exceed the range of array elements sometimes. So actually there can be many unexpected events when the programs are executed. Okay, so these unexpected events need to be detected, and the unexpected events need to be reported to operating systems. Okay? So it is this process is so unexpected events. So these events are called exceptions, and then so I also explained. So unexpected events need to be firstly detected by processors, okay, so by hardware, and these detected events need to be reported to the operating system. Then operating system needs to handle unexpected events. So for example, this is the divide by 0, and then if the divide by 0 is reported to the operating system, then operating system just execute some defined handler, and then we can get the result like it's an exception. Then divide by 0, and then program will be terminated sometimes. So this is the required process, and then also these exceptions need to be supported by hardware. So as I mentioned, it should be detected, and then it should be reported. Okay, and then these processes are called exception handling, and then these software. So when the operating system receives the exceptions from hardware, then operating system needs to execute some defined handler task, and then these tasks are called the exception handler. Okay, so these are exceptions. So unexpected events need to be detected, then these unexpected events need to be reported, and then the software, it's the task. The exception handler needs to be executed. Okay, that's how exceptions are handled inside of a processor. Okay. Then what are interrupts? What is an interrupt? So, so I am using this what's this stylus pen, okay, and then if I just touch the touch screen, then you can observe the output. So it's event, right? But this stylus pen is the I/O devices, the input and output devices. So like if we just type the keyboard, so this is the keyboard is the input device, and then if we just type a certain letter, then we can get the result, right? But how? This is just the event, okay? So program is running. So I'm using the Windows. I'm using the Windows operating system. So program is running, and then this is the PDF viewer, and then I just touch the touch screen. Then we can get the result like this. And how? Because when I touch the touch screen, then this event is detected by hardware, and then this detection, this event, the event from I/O devices or very slow devices. So the processors are very fast, but I'm very slow. So my typing speed is very slow. So these are the kind of slow events from I/O devices. But if these inputs are given to a processor, then the processor needs to detect these slow events. Okay, detect the slow events. Then if these events are detected, then operating system needs to call some interrupt handler. So that's how my computer responds to my input. Okay, so I/O devices are very slow compared to the processors, and then these touching or some I/O events are very rare events. Okay, but these events also need to be handled. So if this event is given, then these events are called interrupts. Interrupts are detected, then the processor stops the currently running program and call interrupt handler. Okay, and then interrupt handler is executed and then return to the previous program. So, and then also the exception is the same. If the exception is detected, then the program is stopped. And then operating system calls exception handler. So this exception handler is also software. So kind of a bunch of instructions, right? So it's a software, and then exception handler is executed and then return to the original program. So what is it? So I use a terminology call, okay? Operating system calls exception handler or interrupt is detected, then interrupt handler is called. It's the same to jump. Okay, do you understand? So actually, the interrupt or exception. So when the exceptions or interrupts are detected, then a processor or operating system calls handler. Handler is also software. So it's similar to the jump. Actually, jump. Okay, very similar to the jump. And so this is how the exceptions or interrupts are handled in a processor. And then also the clock cycles are wasted by exception handling. It is because it jumps to the other part of the software, and then it returns the original software. It's a jump. But we do not consider some exception handling actually for some performance issues. So so actually I mentioned the control hazard for branch instruction, and then actually we used I also explained about the prediction mechanism. Why? And then also prediction is not easy to understand, but we use these prediction approaches to improve the performance because it's very critical. It's very critical for the performance of a processor. But exceptions or interrupts, actually these events are seriously considered for this some architectural enhancement. So it means that we do not consider. So exceptions and or interrupts are kind of jump instruction, or jump. It's very similar to the jump instruction, but we do not apply some specific architectural approaches for enhancing or improving the performance of exceptions. Why? What is the point? We can apply prediction approaches for improving or for reducing the penalties by branch instruction. But for exceptions, we do not apply the same approach. Why? Those are very rare cases. You understand? So we can frequently observe branch instruction. And the branch instructions are very frequently executed inside of a processor. So it means that if we can improve the performance of branch instructions, then we can dramatically improve the performance of processors. And it's also very critical for the performance of processors. But exceptions or interrupts are very rare events. Okay? And then also it's very slow. And it is handled by software. Because these events are very rare events, so we do not apply any prediction approach or any architectural solutions for these exceptions or interrupts. Okay, because these events are very rare events. Okay, so we can find some the baseline approach like if the event is rare, then it should be managed by software. Okay, if the events are very frequent, then it's managed by hardware. Okay, so it's some baseline approach. Okay, because the slow also so slow, it's managed by software, and fast, it's managed by hardware. So this is the common approach now when we manage the computer system. So it's a rare event. It's handled by software. So it's a frequent. Those are frequent events, and those events are managed by hardware. Okay, so exceptions are very rare event. Then, but it's also issued to be supported by hardware. So, and then actually exception handling is a little bit difficult. So which means that sometimes we apply some specific rules for handling exceptions in hardware. Okay, so I will explain about how the exceptions are handled in the hardware in the next lecture. Okay, any question? So in this class, we handle the branch prediction. So I hope everyone can understand the branch prediction. What is branch prediction? Okay. 감사합니다.